Okay, so we're in chapter 2 now in your book. When we finished the last chapter, we defined this thing called a derivative, and we had different ways to express it. Here's just two of them. One was this difference quotient, the limit as h approaches 0, of f of x plus h minus f of x over h. Or we also said sometimes in terms of two different points, the limit as x1 approaches x sub 2, f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. And there are other ways to actually write this. Your book uses several different versions. If you look online, you'll see different versions. Sometimes we use t's for time as opposed to x's. Ultimately, though, we understand this or this, however you choose to write it, represents a secant line, in particular the slope of a secant line. Here it's more obvious. Those are my 2 points. Those are the x's, those are the y's. Change in y over change in x, it's the slope of a line. Those are average rates of change. Once we do this limit trick, those average rates of change become instantaneous rates of change, and my secant lines become tangent lines. And we called this thing a derivative, and now in this chapter we're going to start working with derivatives, seeing how we calculate derivatives for different functions, and then look at different applications applying derivatives. There's a lot of notation involved here, but before we actually do the notation to see how this can be worked out, if this idea of a derivative makes sense, then it should agree with everything we've done up to this point. Meaning, suppose we have something like this. F of x equals 2x plus 3. That's the equation of a line. We all know the rate of change of a line. It's the slope, which is m is equal to 2 here. If this derivative measures the rate of change, then it should certainly measure the rate of change of that line and give me the rate of change of the line, which is the slope. So we can at least test this definition and see if it works with that. And if it does, while it's not a proof of it, it at least tells us that this seems like a definition that we can use and understand as a rate of change. And you're going to be doing a lot of this, so we just want to kind of work through this one first. And the idea is we're just going to plug this into that. And as I've said before, there's lots of interchangeable ways to write the derivative. I personally prefer this version right here of the definition, so that's the one I'll use most often, but you can use other ones. The limit as h approaches 0 of f of x plus h, which for us will be 2x plus h plus 3, minus, make sure you put it in parentheses, f of x, which is my function, 2x plus 3, all over h. Solve that out. And I'm actually going to drop my limit stuff just to save space until we take the limit at the end. So here, if I distribute, I get 2x plus 2h plus 3, distribute by negative, minus 2x minus 3, all over h. Now, cancel like terms or whatever, 2x minus 2x, 3 minus 3, and I'm left with 2h over h. The h's cancel, and I get 2. Now, keep in mind, for this one, since all the h's are gone, I am actually done. But in general, once we get to this point, now we apply the limit. So I get the limit as h approaches 0 of 2, but the limit of a constant we know is just the constant 2, which is the slope of the line, so it's what we actually should get if this idea of a derivative in this definition is giving me the rate of change, which is good. That's a good thing, and it means that we can now apply this to higher order functions and be confident that whatever I get once I do all this algebra out is the slope, if you will, the rate of change, the instantaneous rate of change of the given function. We're going to do a couple more examples because being able to work out all of this algebra is important. I know we've already done some of it with your limits, but now we're kind of formalizing it all. We want to make sure we're clear on it. But as far as notation goes, we call this limit derivative, and the way we write it is f prime of x. That's just like, I guess on your keyboard, if you were typing it out, probably an apostrophe. But it's just f prime. That's called prime notation. F prime of x. It means the limit as h approaches 0 of f of x plus h minus f of x all over h. And this just means the derivative of the function f of x. So we will generally have a function f of x, like we just had 2x plus 3, and then we'll find f prime of x, the derivative, which for this one we now know is 2. And that will kind of be the goal here. Given a function, find its derivative by running through all the algebra there. But that's just one way to write it. Again, that's called prime notation. But there are other ways to write it. If you ever heard of Gottfried Leibniz, he was a mathematician who lived around the time that Isaac Newton did several hundred years ago. And he's one of the founders of calculus, the ones we give credit to, Gottfried Leibniz and Isaac Newton. And we have what's called Leibniz notation. That's a Z. Because this is the way he wrote his notation for derivatives. And I will point out, I actually write my Leibniz notation different than the way your book does because there's different ways to do it. I personally prefer dy dx. And this just says the derivative of the function y with respect to the variable x. Dy dx. If we maybe had a function with respect to time t, then I could write dy dt, the derivative of the function y with respect to t. A lot of times with function notation, and I'm checking all my notes to make sure I write all the notations your book uses. For functions, we also use f, so we can say df dx. Same principle, the derivative of the function f with respect to x. This thing on the bottom is important. That tells you your variable that you're taking the derivative with respect to. That'll be more important later on as we get to more complex stuff. But this just tells me what my variable is. Here it's x, the derivative with respect to x. Here we write the variable on the bottom. Let's see. Your book will also write d dx f of x, which is, again, this d dx means the derivative of the function f of x with respect to x. There's lots of ways to write it. Don't get confused or lost. There's just lots of different mathy and sciencey people, and they choose to find their own shorthand or slightly alter existing shorthand, but they all mean the exact same thing. Ultimately, the main two that we use will be the prime notation, f of x, f prime of x, and Leibniz notation. And we'll either use dy dx or df dx. And I'm just going to tell you personally, I prefer dy dx, even though your book uses df dx. But we can make them interchangeable. Okay, so let's see. Maybe one more example, just to see this worked out. Suppose I have the function f of x equals x squared. I want to find f prime of x. Well, then by definition, f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. And you are going to be finding a lot of these derivatives using this definition. You don't need to write this out every time. I'm just doing it for formality. You can just immediately jump into applying. Again, I'll drop the limit until I get to the end just to save space. F of x plus h, that would be x plus h squared minus f of x, which is x squared, all over h. And it came up when taking limits on your homework before. How do we kind of go about solving this out? When, like, if I plug in h here, I'll end up getting h squared, I'll get x squared minus x squared over 0. So I'll get 0 over 0. The algebra for these has to work out simply. And all you do is simplify everything out as much as you possibly can, and then the algebra will just naturally work out. When I was a student, I didn't understand that, so it made it harder. And bear with me if your camera jumps around for a minute. My cats are jumping on the cat tower again. Let's see if I can convince him to leave. Go away. Okay, he's gone now. Okay, so now I'll just FOIL this out. All of you can FOIL that. You get x squared plus 2xh plus h squared minus x squared all over h. Here, x squared minus x squared cancel, and I'm left with 2xh plus h squared all over h. Now there's a common h here, here, and here in all three terms. I'm going to cancel it out of all three terms and then apply the limit. So we'll take the limit as h approaches 0. This h canceled. One of each of these did. So I'm left with 2x plus h. Now, as h approaches 0, that h approaches 0, and my limit becomes 2x. And now again, when we did this with a linear function, we got the slope of the line, which makes sense. We're not going to spend a lot of time finding derivatives of linear functions. We will occasionally, but the derivatives of linear functions are just the slopes, so we already know how to do that without taking the derivative. So that's kind of not as fun. We're going to be spending our time with higher order functions. So does that make sense? And what does that mean? Now I'm taking the derivative, but this derivative has a variable in it. It's actually a function itself. And does it make sense that there should be an x in there? There should be a variable in there. And we're just going to finish up this video by looking at that. So, suppose I have the function x squared. We all know the graph, it looks like that. For the sake of argument, pick the point 1, which will be 1, 1, because it's a square function. What is the slope of the tangent line right there, which we said is the derivative? It is that limit. What would the slope be there? Looking at it, I don't actually know, but it's definitely positive. If I say my derivative is my rate of change and it's equal to 2x, well, here at the point 1, 1, x is 1, and the derivative there is equal to 2. Let's write 2 right here. It's positive. What if I look at the point over here, we'll say 3, 9. Clearly, this is a parabola. It's getting steeper. Does that actually make sense right here? Well, if my derivative is 2x, at 3, if I plug in 3, I get the derivative is 6, which means my slope is steeper. It makes sense. What if I pick a point over here, say negative 1, 1? If I draw the tangent line, here the slope is negative, but if my derivative is 2x, at negative 1 I get negative 2, I get a negative slope, which I should. If I look at the point 0, 0, clearly at 0, 0 at the vertex, that's horizontal. Slope is 0, horizontal line. If I plug in 0 here, I get 0, which means this is why your derivatives are functions, why they have variables in them, because the derivative changes. Now that we're not talking about lines where the slope is constant, the derivative changes at all the different points, so we need a variable in there to account for the change in the slope, even though it's not a slope anymore. I personally just think that's really kind of cool. In the next video, we're going to look at some properties of derivatives, maybe work through 1 or 2 more examples using this definition because you're going to need to, and then we're going to go on and do some more stuff from there. We're going to spend a lot of time working on these derivatives. They're really important. They're the bulk of what we're going to cover in this class.